This video is a lesson on the connection between your location on Earth and what you can see in the sky. It's Roman numeral 1 in our unit outline. More specifically, it's help with these first few objectives and some of the first homework problems that you will find. When we look at the sky, think about it. You go out in the nighttime sky and you look, it's like you're inside a bowl, on the inside of a bowl looking out. So you see half of a bowl, or you see half of a sphere. The inside of a bowl would be a hemisphere. So we can only see one half of the sky, so to speak, at a time. We saw the model of the celestial sphere. We can imagine we're surrounded by stars, but we can only see half. So the question is, what half? And part of that answer to that question is it depends on where you are on Earth, your latitude. It also depends a lot on what time it is, what date it is. So what day of the year is it? Is it 8 p.m. or 11 p.m.? Those things matter. The one that's kind of surprising is it doesn't matter that much what your longitude is. So that might kind of surprise you, but longitude does not have much of an effect on what you see. If you have your latitude and the date and the time, then we can fairly well predict what you're going to see in the sky. This diagram is helpful in trying to understand what is the connection between your latitude and what you see in the sky. So I have a diagram here, and of course you can see that's the Earth in the center with the North Pole facing up. And then the circle around is the celestial sphere. So we imagine all the stars are on this gigantic sphere. Not true, but it's what we're going to see it as. Directly above the Earth's North Pole, there's the celestial North. Directly above the Earth's equator is the celestial equator. Keep in mind that if you took the coordinates on the Earth and you just kind of expanded them out into space, it's the same coordinates with different names and different units for right ascension, but that's a minor detail. So if you imagine taking the coordinates on the Earth and expanding them out into space, the latitude on Earth would turn into the declination on the stars, and the longitude on Earth would turn into right ascension. The celestial, the Earth's equator becomes the celestial equator, and so on. But now, if you think about what is going to happen for an observer on Earth, what if I'm this person who's illustrated here on the northern hemisphere? So, this part of my diagram, I've got my northern hemisphere guy, and there's also somebody down here. Looks like they might be a little bit in the southern hemisphere. So what's going on with them? Well, if they point straight up, they're pointing in different directions. So I have that here. Our guy in the northern hemisphere, he points straight up and he says, that way's up. He might be pointing at a certain star. But our other person here in the southern hemisphere, he points straight up. He may be pointing at a different star, would be pointing at a different star. There's no way they're pointing at the same star. So where is straight up depends on where you are on Earth. Your latitude is going to control what part of the celestial sphere you're looking at. Look at this diagram. The person in the northern hemisphere would have a better view of the north part of the celestial sphere. The person in the southern hemisphere would have a better view of the south part of the celestial sphere. So what exactly is the connection? Well, latitude connects to declination because they're essentially the same idea. This is a picture of a physical model, an actual physical model you can hold in your hands, showing essentially what I was trying to show in the previous diagram in the PowerPoint. And you can see here we have a clear plastic sphere, which represents the sphere of stars. And then inside that sphere, at the center of that sphere, we imagine the Earth to exist. So we're on the inside looking out, but this view is if we could have a godlike view out from the outside looking in. If you look closely, you can see on the sphere the Big Dipper. That's kind of fun. So right up here, There's some stars that I recognize as a Big Dipper, but it's inside out. It's reversed because we're on the other side looking in instead of on the inside looking out. You can also see the United States. Let's zoom in a little bit. And if we look closely, we can see we seem to be kind of centered on St. Louis, Missouri, something like that. And notice, if we're looking at St. Louis, Missouri, or somewhere in that ballpark, looking at a point on Earth that has a latitude of 40 degrees. And then, oh, what do you know? Look at this. Uh, on the clear sphere of stars, we're looking, oh, that's declination 40 degrees. So, if we're looking at a point on the Earth that's 40 degrees, and then here's this declination 40 degrees, well, that kind of makes sense if you think about it. Again, it's like you took the lines on the Earth and you blew them up like a balloon out into space. Here is side view, exact same setup. I didn't move one thing. And this is a side view of our observer. Let's imagine somebody is standing in the United States, say St. Louis, Missouri. They have a latitude of about 40 degrees, and then they're looking at the celestial they're looking at the celestial sphere, and they see a certain hemisphere. You might have noticed this blue ring inside the model. It makes it right in here. That makes it kind of look like Earth has rings. Well, that ring, that blue plastic ring inside the model, is actually intended to represent your horizon. So if you think about it, the person's view would be centered on that ring if I tilt it, and you can adjust the tilt. And I have it adjusted correctly to show this observer's horizon. So if they look at the celestial sphere, this is the half of the celestial sphere that they are going to see. And when they look straight up, they're going to see this point directly above, which is going to be their zenith. So their zenith is going to be right up at the top of that green line. And well, hey, we just saw that that was going to be 40 degrees, and they're at 40 degrees latitude. They're at 40 degrees latitude, and when they look straight up, they're going to see 40 degrees declination straight overhead. That's going to be their zenith. So now we're going to look at the view of the sky as simulated by Stellarium, and there are lots of programs that can do this for you. And we're imagining the view of the sky for a certain observer on Earth. So there's a lot going on in this slide, but check it out. So over here, we have kind of a side view. This is going to imagine somebody standing on the equator right now, halfway between the North Pole and the South Pole. Notice the time, midnight, January 14th, nothing special about that, but just a particular date and time. And over here, I'm showing their latitude. So that's where they are, latitude 0 degrees if they're on the equator. The computer is showing us their horizon. Notice there are these east point on the horizon, south point on the horizon, west point on the horizon. Notice the green line is labeled meridian. So this is their view on that date, and they can see the sky and the stars, and some of them are labeled. This is their horizon. And then there's the south point on the horizon. So I already pointed those out. I'll just add those labels, make them easy to see. And then this point would be straight up for the observer. So, and that would be the center of the circle. Maybe it doesn't look like the center, but it's because of just kind of the distortion of the screenshot. So straight up is right here. And then this is the celestial equator. That's the constellation Orion right here, which I kind of highlighted, and I'm going to highlight in these next few slides. So this is the celestial equator, which goes right through the center of Orion, the constellation Orion. And as we said just a minute ago, if you're at 0 degrees latitude, when you look straight up, you're looking at 0 degrees declination. Well, that's the celestial equator. So I hope you get what we're doing here. We're just kind of imagining, okay, if I'm here on Earth, here's what I see in the sky. And now our person is going to take a journey. Notice over here, I moved them. Where are they now? 10 degrees north. And notice my view changed. Now, when I look straight up, that little red cross is still their zenith. They're looking at 10 degrees. They're looking a little above the celestial equator. If we keep going up, so now I'm at 20 degrees. Notice over here, I keep moving around the Earth. If I keep moving around the Earth on the same date and time, and just increasing my latitude, I get a better and better view of the north part. So north of the celestial equator would be above the line in my diagram. Remember, the blue line is the celestial equator. And so I'm basically just starting to get better and better views of the northern part. If I'm at 30 degrees latitude, I'm looking at 30 degrees declination, which is this line which I'm tracing right here. So that's 30 degrees declination. I'm looking straight up. I see 30 degrees declination because I'm at 30 degrees latitude, and so on. So we can imagine continuing on 50 degrees north. You're somewhere in Canada, maybe. The sky looks like this. Keep heading north. You're taking a journey to the North Pole. It's fun when you get to the North Pole. What are you going to see if you're at the North Pole? You're on the Earth's North Pole. You look straight up, you see the celestial North Pole, which would basically be Polaris. Polaris is the star hidden by the little cross, although not exactly at the center. Polaris is really close to that point, and you will be looking straight up. Um, so this is an interesting place to be. Very few people ever get to go there, of course. Did you notice what happened on my horizon? This is kind of quirky, but hey, if you're on the North Pole of the Earth, everywhere you turn is south. You can't go anywhere but south. That's a fun thing to think about. Kind of hurts my head a little bit. Let's keep going. So quickly, let's go the other way. So now I'm back on the equator. Notice I'm back to 0 and back to our original view where Betelgeuse and this celestial equator are straight overhead. But if we go south, of course, the opposite things happen. So now I'm south of the equator, south latitude 30 degrees, now south latitude 60 degrees, and so on. So I can get all the way to the celestial South Pole by going to the Earth's South Pole. So I'm looking at the celestial South Pole would be the center of my view, and I have nowhere to go but north. So if you look at the horizon, it's labeled north in all directions. So this would be the view from the South Pole. What is this really bright thing, and why can I see the grass all of a sudden? Well, that's the sun. On this particular day, if you go to the South Pole at midnight, the sun is up. So that's what the program is simulating for us. All right, so now we're ready to summarize, hopefully, what you've noticed and figured out with the stuff that I've shown you. We're back to our original diagram, effective observer's latitude. So if we look at the night sky, what do we see? Well, here are the points we've already talked about. Connected to the Earth, celestial North Pole, celestial equator are extensions of the Earth's poles and equators. And then if I look up, my view is controlled by my latitude. So remember, latitude is how many degrees up from the equator or down. Negative latitude would be down or south latitude. And then we've talked about this. If you look straight up, you're looking at your zenith, and your zenith is going to be your declination. So there's a one-to-one correspondence between your latitude and your declination. It's the same thing if we're talking about your zenith. Like if you look straight up, you are looking at a declination that is equal to your latitude every time. That's always true. I hope the diagram makes it clear. We've also tried to illustrate it in the other things. So I hope that's starting to make sense to you. Your zenith is 90 degrees away from your horizon. So if I draw a line perpendicular to that one, now that's my horizon. And here I've labeled for this observer. If they face the north, they'll be looking to the left in this diagram, so that would be the north point on their horizon. If they're looking towards the south, they would be facing to the right in this diagram. And so I've labeled that south horizon. We also have an interesting thing. So the altitude of the celestial North Pole would be how high the celestial North Pole is from the north point on your horizon. The North Pole in on the sky, the celestial North Pole has a convenient star. Remember, Polaris is really close to the celestial North Pole. So if we were looking at Polaris and we pointed towards the north horizon and then pointed towards Polaris, Polaris and the celestial North Pole would have a certain altitude, and that's shown here. So watch what happens now. I'm just going to tilt this diagram. Boing, boing, boing. And now we're getting the perspective of the person. So now straight up for my person is straight up in my diagram. I just rotated the whole diagram. So now the altitude might make more sense to you. Like if I'm looking towards the left, I'm looking north, and I would see Polaris at a certain altitude above the horizon. Let's summarize in words. The declination of an observer's zenith is always equal to the observer's latitude. That's something you should know. Because of this, if you think about it, if you're in the northern hemisphere, you can only see so far south of the celestial equator. And there's a rule here. We haven't really talked about this in the previous slides, but if you're in the northern hemisphere, you can't see south of a certain declination, and that kind of limit of your view would be your latitude minus 90 degrees. For example, if you had a latitude of 40 degrees, 40 minus 90 is negative 50. You would not be able to see below 50 degrees, negative 50 degrees declination on the celestial sphere. We'll see this in some other places later in the show. Here's an interesting point. The altitude of the celestial North Pole is always equal to your latitude. These words, they all kind of blur together. There is a similarity between latitude and altitude, but then there's also this equality, which is remarkable. So if we're looking at the celestial North Pole and we happen to have a latitude of 40 degrees, the celestial North Pole will have an altitude of 40 degrees. If we're looking at the celestial North Pole from a latitude of 10 degrees, the celestial North Pole will have an altitude of 10 degrees. And so this is true wherever you are on Earth. That's always true. And then we also have an interesting idea that because the celestial North Pole is typically above your horizon, unless you're on the equator or south of the equator. But if we're talking about the celestial North Pole, we spend most of our lives in the northern hemisphere, then we're going to see certain stars that never go below the horizon. They're close to the celestial North Pole. The celestial North Pole is always in the sky, always at a certain altitude. So if you're within a certain region of the celestial North Pole, those stars never set. They are called circumpolar stars. So on this slide, listen carefully, and I want you to try this. So you can pause the video and take as much time as you need. Pause the video on this slide so you can see the directions. Open Stellarium Web in a browser on your laptop and follow the instructions shown here. And this is going to be practice with the concepts that we were just talking about. And I hope that this would help you see the connection between the concepts and actually doing it. It's nice to imagine you are actually looking at the sky. Stellarium Web helps you do that, and you can play with the settings. So I've got this little activity. I'll just give you some time to try it. All right, so I hope that you did what it said to do in the previous slide. And if you did, hopefully you could tell that, okay, when time goes by, certain stars in the sky never go below the horizon. They're always up. They move in a circle. This is an actual photograph, and a time-lapse photograph where we can see a certain number of hours have gone by. This would probably be several hours. We look at the length of the arc shown there, and this arc looks like, I don't know, maybe a quarter of a circle. So this is several hours, maybe 6 hours. I don't know. This took a while to make this picture. But we can tell that the stars are spinning around a point and they leave these circular paths. And there's a point right here and an arc really close to that. That must be Polaris. So this is a picture of what it actually looks like. The altitude of Polaris, wherever you are, would equal your latitude. So this, we have a hint here. Wow, we got a cactus. Where do I find cacti? Maybe this photograph was made somewhere in the southwest in the United States at a relatively low altitude. This looks kind of low in the sky to me. And if you were at a low latitude, like 30 degrees, Polaris and the celestial North Pole would be 30 degrees above your horizon. And stars that are within this shaded region that I've added here would never go below your horizon. They would become invisible during the day, but they would actually never set. So this is called your circumpolar region. And these are basically the part of the sky that's near the celestial North Pole, but never sets. Here's another similar picture, and this appears to be higher. This must have been made from a higher latitude because the celestial North Pole seems to be higher in the sky. This would be a bigger circumpolar region because more of the sky is staying above the observer's horizon in this location. The next few slides are going to show a hypothetical journey for an observer around the globe, sort of. So I've got an observer here. I have their latitude. I have a description of where they are. And then we're imagining the celestial sphere and certain stars. So you might try to find these on a star chart. All of these stars kind of line up. Polaris, Capella, Betelgeuse, and Canopus. This bottom one down here is Canopus. If you were on this place, latitude 90 degrees, you look straight up, you see Polaris. Betelgeuse would be low in your sky near the horizon. Capella would be pretty high. But now let's change locations. Here I am in Quebec at a latitude of 60 degrees north. Betelgeuse is now higher in the sky. Polaris is lower in the sky. Now Polaris is closer to the horizon. Polaris would have an altitude of 60 degrees. Capella would be nearly straight overhead. Capella has a declination kind of close to 60 degrees. And so on. So if we keep going around, if I'm in Charlotte, North Carolina, that's similar to being in Knoxville because the latitude is the same. 36 degrees north is our latitude in Knoxville. Charlotte would be pretty much the same. And you can try this in Stellarium if you want to. You can go to these places. All the ones that are named here are ones I think that you can search for and find in Stellarium. So if you want to, you could open up Stellarium and do these same things in Stellarium. Notice now Capella and Betelgeuse are both high in this observer sky. Polaris is kind of low, 36 degrees above the north horizon. And Canopus would be right on the border, hard to see, right on the horizon. If you keep going, go to the equator, Ecuador. Ecuador. And then now you're going to look straight up. You will see Betelgeuse high overhead. Betelgeuse would be very high in your sky at this point, almost at your zenith. And then Polaris is now right on the border of your limits of your view, right on the horizon, hard to see. Polaris would be pretty much invisible from the equator. Canopus would be pretty high in the sky. So now you would have a pretty good view of Canopus. And so on. If we keep going around, our view keeps changing. Somebody in the south hemisphere, 30 degrees south of the equator in Chile, would have no view of Polaris, never see Polaris. And Canopus would be a star that would pass really high overhead. Capella would be a very low star in the sky and would be hard to see. All right, finally, the last few slides in this PowerPoint, we're going to focus on Knoxville. What does it look like from Knoxville or anywhere at the same latitude? So I mentioned Charlotte has about the same latitude as Knoxville. pretty much anywhere on the globe, even around the world. I want to say Tokyo has a similar latitude. So different places on the globe would have similar latitudes, and they would see pretty much the same things you're going to see in the next couple of slides. Here is a map of the celestial sphere, kind of a globe view of the celestial sphere. Here's 0 degrees, the celestial equator, and 36 degrees declination. If you live in a place that's 36 degrees latitude, north of the equator, only stars that are along that line would ever appear at the zenith for that location. If we, here in Knoxville, if we look straight up, we would only see stars that are somewhere on that line on a star chart. Stars, here, imagine a cap on the celestial sphere. Stars in that region from 54 degrees up, above declination 54 degrees, are within 36 degrees of the North Pole and are always above the horizon. This would be like our circumpolar region for Knoxville, or anywhere that has the same latitude as Knoxville. So we can always see those stars. Those are always visible. They might be turned a different way, but we'd always be able to see that little cap of the celestial sphere. And then on the other side of the celestial sphere, I colored this red. There's an anti-cap, I guess you might say, and we basically can never see those. Those are stars we never see. Those are stars that are within 36 degrees of the south celestial pole. They're never going to come up. Just our viewpoint is we never get to see those stars. There's a famous asterism there, the Southern Cross, which you might have heard of. Well, too bad we never see it in Knoxville because it's always below the horizon. Here is same idea but different viewpoint. So now we're looking at a star chart and we're centered on the celestial North Pole. Here's 36 degrees declination, and here's our circumpolar region. So this is kind of exact same idea but just different viewpoint. We see stars that are at the zenith from Knoxville would be on the yellow dashed line. Our circumpolar region, this is the part of the sky that we can always see in Knoxville. Here's the opposite view, looking at the celestial south pole. There's a little region that we never see in Knoxville. Boo-hoo. We don't ever get to see those stars. I need to go south of the equator. I have been south, but not super far south. I think the farthest south I've been was in Hawaii or the Keys, but I've never been south of the equator. So there's a certain part of the sky I've never seen. That makes me kind of sad. Okay, so the final slide here in our program, our video today, is a set of instructions for doing one more activity with Stellarium Web. So I'm just going to put these bullet points up here, and I'm going to challenge you to try to show everything that we were just talking about using Stellarium Web. So what you're going to do is open up the program, get a star chart, which you should have, a paper star chart or any other star chart. You can find one online, but just pick some random star. It doesn't matter what star it is, any star you want. Just pick a star that has a name, one of the more prominent ones. Use the chart, the paper chart, to determine where it is, declination. Then in Stellarium, make your location a latitude that has a value equal to the declination that you chose, the star that you chose. Turn off the atmosphere in Stellarium Web, turn on the azimuthal grid, and then experiment. Find a date and time when the star that you chose gets close to the zenith. It should get really close to the zenith because that's what's supposed to happen. If you're looking at the zenith, you should see a star there, or if you see a star there, it has to be on a declination equal to your latitude. So you can test that idea. You also can test the idea that the altitude of a celestial pole should equal your location on Earth. So if you can see the celestial North Pole from wherever you go, try to determine its altitude and see if it's close to your latitude. You can check your latitude in the location box in Stellarium. You can check the altitude with the grid, or you can also click on something and look in the information box and it will show the altitude. So pause the video here and try these things. And that's the end of this lesson. You can check yourself. What you should find with the program is, okay, everything we talked about in this video works